My computer doesn't crash in the next hour, I'll be very happy, but lately it's been crashing, so that's what you're experiencing right now. So my name is Jeff Bilmes, and I'll be talking, as Fred said, on speech, language, and machine learning. I guess what I'm going to do, traditionally what you probably are used to seeing is a standard sort of textual outline. And what I'm going to give you instead is a graphical outline, because some of what I'm going to be talking about are graphical models. So basically what you have here are essentially a set of general areas, speech, language, and machine learning. And I added an additional one, high-performance computing, which is some work that I've done in the past. And then, so you have general areas up here on the top, and then specific applications, in some sense, of these general areas that I've worked on. And then it's a bipartite graph, and the edges in this graph correspond to the topics that I'll be talking about in the next 15 minutes. And what we'll be doing, for the most part, is starting from left to the right. So we will start by essentially hitting each one of these edges in the graph as we're moving to the left. And we'll start, in fact, by talking about speech recognition and robustness to noise. Okay? And we'll be referring back to this figure to give us our roadmap of where we are in the talk. Okay. So, speech recognition and robustness to noise. So, as some of you might be aware, speech recognition is an important problem, and it's a difficult problem. And the difficulty of the problem is often characterized by the size of the vocabulary and the type of speech that you're actually trying to recognize. And one of the areas where it is still the case that small vocabulary, meaning that the number of words you're interested in trying to potentially recognize in your system is on the order of maybe 10 to 1,000, where small vocabulary is still important, is in the area of noise-robust speech recognition, or extremely low power or low computational resource speech recognition, where you have a portable device like a cell phone or a PDA or a watch or a pendant, where you essentially have to devote as much of your design resources as possible to building cheap and effective systems. The critical design issues here are, as I said, low resource. And so we want to have systems that have very low computational demands and have small memory footprint, and that work in highly noisy environments. So when you're walking around with a cell phone, for example, you want it not to recognize you as saying calling home when a bus drives by, say, which is probably not good. So this first bit of work that I'm going to talk about very briefly is entitled MBA Feature Post-Processing. This is work that I've done with a student, Jiaping Chen. And it's a very simple idea. So the idea here is to do something that's extremely simple but effective at the same time. And what we do is it's a feature post-processing method that consists of the following very simple 3 steps. Subtraction of the mean of the speech vectors, divide by the variance of the speech vectors, and temporarily smooth the speech vectors by an ARMA filter. Now, this particular ARMA filter has degree m, so it's got an FIR component and an IR component, and it has, for the case of m is equal to 2, sort of a low-pass flavor to it. It has this phase characteristic, and it has a very simple implementation. And the implementation, in fact, doesn't even give you the idea of how cheap it is to compute this thing. So to compute this filter, basically all you have to do is have an array with a single scalar temporary scanning over your signal, and you can just basically sum up the values, divide by 1 over 2 over m, or divide by 2 over m plus 1, and then substitute back that temporary in. So it's an extremely cheap method. And at the same time, however, it's actually extremely effective. So the way it was motivated was by essentially something that doesn't always work, but in this case it did work, which is just a visual inspection of speech features, which is looking at, here's an example of a speech feature trajectory over time in clean, and then under various noise conditions. So this is under a signal noise ratio of 20 dB, 15 dB, 10, 5, 0, and -5. And you can see that the difference between the clean and the noisy case corresponds to essentially a shift, which is where mean subtraction changes things, a scale, which is where variance normalization changes things, and then basically the existence of high-frequency noise, which is where this low-pass filtering helps. And it's a very simple idea, and it's not even that new in the sense that mean subtraction and variance normalization are very, very standard methods, and the only difference that we're doing here is this temporal smoothing. But when you do this, you can see that even in the noisy case, the speech features are much more similar to the clean than they are in the noisy case. So we tried this on a standard noise robust speech, a noisy speech corpus, the Aurora 2. And you can see, that's probably the best thing to look at are these two numbers here, where the raw state-of-the-art baseline are these numbers, and the accuracy improves at each level of adding mean subtraction, mean variance normalization, and adding the temporal smoothing, and basically you get better. I guess another summary of, the question was, does this actually work just for one set of features? We recently tried it on 9 different set of completely different speech feature types. The specific feature types don't matter so much, but that you can, the fact that they're different is important, and you can see that in each case it gets pretty much better, going from raw features, the original features, mean subtraction, mean invariance, and ARMA filtering. In each case, it gets better in the noisiest of cases and in the 0 to 20, basically at the medium case. Okay, so that's noise robust speech recognition. It's a simple technique. Basically, the story was that it's something that should be applied to every speech recognition system where you want robust to noise. The other sort of this is sort of a similar area, low power software and speech recognition. Again, the idea is to try to develop speech recognition systems that require very few resources. And so I've been working on a number of different efforts in this area. The first one is essentially the idea of trying to have a speech recognition system, when it's stored in memory, consume as few resources as possible, in the sense of have it be compressed, the parameters of the speech recognition system, compress them down to as little as possible. And the way that that works, essentially, is by taking parameters of your speech recognition system and quantizing them and then storing them concisely in memory or in ROM or something. And so that's basically a vector quantization procedure. And the first question you might have is there in fact correlation between the parameters of a speech recognition system? So this isn't vector quantizing the parameters, the speech itself, it's quantizing the parameters of the system itself. And the question is there correlation? And indeed there is, and this is showing basically typical correlation patterns between vector element pairs of the parameters of the speech recognition system. These are the variance parameters of the speech recognition system, and these are the mean parameters of the speech recognition system. And these are the same if we were to just look at random vectors of means and variances. And so you can see that in the random case there's no correlation. And the correlation in this case is measured in mutual information, so that it's in units of bits. So basically, as the mutual information increases, there's more correlation, and so therefore we should be able to quantize better. So we evaluated. I unfortunately don't have time to go into the details of any of these topics, so I'm going to be going through each one of these topics fairly rapidly. So you'll have to. I'm just going to be covering, in some sense, the very high-level aspect of each one of these things. We evaluated various clustering methods of the parameters of the speech recognition system and vector quantized each one of these clusters, and found that using a number of different techniques on multiple different speech recognition systems, we were able to get it down to the case where each parameter, each individual scalar parameter of a speech recognition system required only about 5 to 6 bits. So this is basically looking at the total number of bits per parameter in a speech recognition system. So if you're using single precision floating point arithmetic, then you'd use 32 bits. And so starting from 32, our word error rates were, in this particular case, this is on Timit, our word error rates were about 13%. And as you use fewer and fewer bits, the word error rates increase. But using these various clustering schemes, we got away with, in this particular case, about 10 bits per parameter before the word error rate started increasing appreciably. And in another database, this is on the phone book, which is a telephone database, we were able to use the same scheme. And if you're doing isolated word sort of telephone speech, then you can get down to 4 bits per parameter. So really, each parameter only needs to have about 16 different values. And with 16 different values, you can do as well as when you have 2 to the 32 different possible values in the single precision floating point case. So it's actually quite amazing that we can get away with so few bits in our speech recognition system. Okay, but that's just the parameters of the speech recognition itself. You might next ask, okay, what about the actual running of the speech recognition system? Because once you've got the thing stored, you need to expand it out and actually do speech recognition. So what we did here was try to essentially take the entire speech recognition process. And you can think of the speech recognition process as a big data flow graph. Basically, you've got a set of inputs which consist of your speech signal going through this big data flow graph, where each data flow graph consists of a signal and possible operations on the signals like addition and multiplication and other sorts of operations. And try as much as possible to replace each signal by a very low bit quantized representation, and then each operation by essentially a lookup table, by a low bit ROM, so that we can fit everything, the entire speech recognition system in as small of a memory footprint as possible. And we did this, and there were actually two sort of interesting aspects of this process that are worth mentioning here. Actually, three aspects. One is when you're doing things like dot products. So when you're computing Gaussian densities, you need to do a dot product. You're essentially doing multiply accumulates. And so you need essentially a lookup table to implement a multiply operation and a lookup table to implement an accumulate operation. But the multiply is actually pretty easy because the dynamic range of each of the operands in the multiply are roughly the same regardless of where you're doing the multiply. But for the accumulate, the problem is that the dynamic range as you're doing the accumulate under various strategies changes. Think about if you have got a loop for doing a dot product, as you're accumulating these squared values together, the value is going to shift, basically, depending on the number of things that you've so far accumulated. And so in some sense, you could say that the entropy of the operands are fairly high in that case. And there are a number of different schemes that we tried, including basically having lookup tables using this idea that I just mentioned, where you just have this linear chain of accumulators with growing dynamic range, or a tree-based scheme. And then for each one of these particular diagrams, you have an option of a different number. How many lookup tables do you have for each one of these operators, and so on and so forth. And then the next key thing, which is in some sense more interesting, is when you're doing the alpha computation or the forward computation in the speech recognition system, you've got something that is even worse than this, because now what you've got is essentially a bunch of probabilities that are being multiplied against each other, multiplied with respect to each other. And as the time of the signal increases, basically the dynamic range decreases exponentially with time. And it's even worse in the sense that there's no fixed upper limit on the dimensionality, because the upper limit is however long time is going to get, and that can be arbitrarily long in the speech recognition system, as I'm sure many of you know. So what we did is we developed a scheme whereby we're actually scaling this forward alpha computation with an exponential such that the dynamic range, rather than falling off exponentially, is linear. It's actually falling off linear now. So you have the same kind of situation that you have here. But at the same time, you can still do a perfect job basically recognizing and figuring out what the best and most likely hypothesis is. So it yielded a significant improvement by doing this exponential scaling. And then the last trick, if you will, that we used in this particular scheme is basically the idea where you don't want necessarily to allocate all of your bits where you have the greatest frequency of value. So when we're essentially quantizing, for example, a probability score, it's the case that if you look at the histogram of probabilities, this isn't the probability distribution, it's the histogram of probability values, most of the probabilities are lower than the maximum ones. And the lower probabilities are the ones that you, in some sense, don't want to allocate all of your quantization mass to, because those are the things that you, in some sense, want to get rid of, since the low probability ones are the least likely ones. Yet standard quantization methods like LBQ would do the wrong thing. It would basically give all of this resolution to these things which are basically not happening very often, or which have low probability. And so we came up with essentially a discriminative quantization measure, where instead of measuring the squared difference between, say, a value x and its quantized value, we're actually scaling the distortion by something that increases linearly with the value itself. So that as the value gets small and large in magnitude, basically the cost of a given distance decreases. So in some sense, you can think of it as like a discriminative quantization measure. And so we implemented all of these things together. we found the best combination of number of bits per parameter, number of bits per operand, and number of bits per operator, using a simple greedy strategy where we're estimating a discrete gradient by the difference in word error with respect to the change in final storage that it takes to store the entire speech recognition system, and have the following results. We have essentially a baseline result, which basically, this is the speed up over baseline, and this is based on an estimate of the number of cycles per lookup table, for LUT for lookup table access. And you can see that as the cycles per lookup table decrease, the speed ups increase significantly. And basically, these are different. Each one of these lines corresponds to a different simulated modern microprocessor. Like this one is, for example, is a modern desktop microprocessor. This one is a very simple processor without any cache. This one is high-end DSP, so if you're interested in implementing this on a DSP, you get this kind of speed-up profile. And the other thing that is worth mentioning is that the final ASR backend, the final system, was able to store all of its parameters in only about 59 kilobits of ROM. So that's an extremely small memory footprint. And when you have such a small amount of memory required, it's pretty reasonable to essentially have 1 or 2 cycles per ROM lookup in that case, because essentially it's smaller than typical L1 caches at this point. So, what is the task? So we tried this on both PhoneBook and on Timid. So in this particular case, we're just looking at, this is Timid results actually, but it worked in both cases. I'm just going to briefly mention this one. So another effort that we were working on in trying to speed up speech recognition systems was in basically, again, in trying to evaluate Gaussian distributions, which in some cases requires a significant portion of the time, where we basically cluster the elements of the Gaussians together in such a way that you can actually predict the resulting likelihood of one portion of a Gaussian given another portion of a Gaussian. And so the basic idea here is that when the likelihood evaluation of one portion of a Gaussian is small, we basically, rather than dealing with trying to go ahead and estimate the rest of it, we just basically predict it by just a simple linear function, which is described here. And that essentially gave us almost no penalty in word error rate increase, basically a 0.5% absolute increase in word error rate increase. But we were getting speedups of like 1.35 or 1.7, 1.8. with corresponding power reductions of maybe 27% up to maybe 40 to 43%. Now, all of the power reductions were, of course, simulated. We used the watch simulator to simulate the amount of power that each one of these systems were taking. So both these results and the speedups that you saw based on the number of cycles per plot for LUT lookup were all in simulated environments using this low-power simulator. Okay, that's low-power software and speech. Okay, so the next thing I'm going to talk about is something it's high-performance computing, and it's the FEPAC high-performance numerical library system. This is work that I did a number of years ago, but because it's been fairly influential, I wanted to mention it at least briefly. And the idea is as follows. Basically, there's this problem, and many of you are probably aware of this, which is that when you want to have high-performance numerical code, whether it's FFTs or matrix multiplies or some other kernel, some other standard numerical operation that you want to work with, it's often the case that on a given microprocessor, you can buy a library from the vendor, whether it's IBM or Sun or SGI or whatever vendor it is that supplies these libraries, and then you can link to them in your code and essentially get high-performance routines out of it. But the problem, of course, is that these high-performance numerical libraries are expensive. They cost at a minimum of maybe $10,000 to $15,000, and then if you're a company, then it's, of course, even more expensive to get these libraries. The FEPAC strategy, which is work that I did with Krista Sanovich and some other colleagues back actually a while ago now, is to essentially, instead of spending $15,000 on a library, we write C code, but we write C code according to special guidelines that are specifically made so that it's not easy for a human to read, but it's easy for a compiler to optimize. So basically the code is written according to special guidelines that basically makes it easy for the compiler to do instruction selection, scheduling, and register allocation, and at the expense of readability. But then at the same time, rather than actually code by hand. So in some sense, we reduce or mitigate the problems of having a low readability by instead writing actually code generators. So we don't write in C directly, we write a generator which writes in C. And then lastly, we write a search scripts that searches over the space of possible parameters within the space defined by this code generator. And this approach we called FEPAC. And I should mention that many of you might have heard of the Atlas approach. Has anyone heard of Atlas? So Atlas is the thing that Jack Dongarra at Tennessee, he's one of these high-performance computing guys, has been pushing. And basically, FEPAC came before Atlas. And in fact, Jack was in my talk when I was giving it at ICS 97. And then he went off and implemented Atlas after he saw the FEPAC talk. So, but FEPAC was extremely successful. And just briefly, so the coding conventions are things like naming registers specifically as local variables so that you remove false dependencies, things that essentially can't be removed otherwise in C programming language. And we use locals, and basically locals can be essentially allocated in registers by the compiler so that we reduce the register memory bandwidth requirements by essentially having things locally where we want them to be. We use things like base plus constant offsets rather than actual increments, because most instruction sets include basically a base plus immediate constant offset addressing mode. So you can essentially get these things very cheaply right away in a single cycle. We expose init operations, again by using local variables. And there are a number of other things and tricks that we do here. This is an example of what the code might look like. This is an example of a 3-tap FIR filter. And in this particular case, these are two C implementations of the same exact FIR filter, where the filter lives in this array, filter 0, filter 1, and filter 2. And rather than doing this, the problem here is that each time you essentially dereference res and then write back to this memory location, the C compiler doesn't know that maybe you're actually writing over the filter, which is bad because there's potentially array aliasing. Instead, what we do is we just load the filter up into as many local variables as possible. And most modern microprocessors have at least 32 floating point registers to use. And why not use them? Why not take advantage of them? And then with these things sitting in locals, then we go ahead and scan over the resulting array. That is much faster. So here's one result. These are the typical kinds of results. There's one caveat about this, that this is an older machine at this point. So you're saying, hey, 250 megaflops, that's not that much. But remember that this was a while ago, and the results are still valid on today's modern microprocessors. So this is a fully optimized Fortran 3-nested loop matrix-matrix multiply routine as a function of the square matrix size and the number of megaflops achieved. This pink line is IBM's $15,000 ESSL library. It's a matrix, their matrix-matrix multiply. And we, based on a sort of not that much of a search, we actually beat ESSL. And when IBM found out about this at the time, they were actually pretty unhappy. But then they are also at the same time they were happy, because they realized that it's actually, you can actually, by searching over the space, and by the ESSL, I should say, is highly optimized vendor tuned specific for this architecture, whereas the FEPAC approach was generic. It could run on any machine. And so it was pretty good. Okay, so that's FEPAC and high performance computing. Next, I'm going to start branching over and talk about machine learning and intransitive game theory. Okay. This is work that I did with Gong Ji and Marina Malia back in NIPS in 01 and 02. Basically the issue is the following, that in many classification procedures it's possible and typically it's often desirable to cast classification problems in terms of a set of binary classifiers. For example, likelihood ratios, which is what we're working on here, but also support vectors in kernel machines and binary neural networks and so on and so forth are essentially binary classifiers. And the question is, how do you achieve multi-class classification versus binary classification? There are many methods that people use in the support vector community, such as ECC, and 1 versus 1 versus 1 versus all, and so on and so forth. What we do is essentially, we've developed a strategy where we utilize the fact that a collection of n-squared binary classifiers might be intransitive. Meaning that if you think of the result of a set of n binary classifiers, it might be the case that, say, A is chosen over B, B is chosen over C, and then C is chosen over A. So that you have essentially a cycle in your winner-loser directed graph. And the question is, what do you do with this? Well, first of all, where did this actually come from? We were working with likelihood ratios. So we have this likelihood ratio, which is an estimate of the true likelihood ratio. And then we had a criterion function which says, okay, how do we find the best constant correction of this estimated likelihood with the true likelihood? So basically, we want to try to find alpha, which best corrects the difference between the estimated and the true, weighted over the training set. And we found that the best constant correction turns out, based on, after a couple of assumptions are made, is equal to the difference between two estimated Kullback-Leibler divergence terms. And this is the result. So obviously, if we get the original likelihood ratio back, then we're not going to have intransitivity. Right? So the intransitivity is going to basically be, in some sense, an indicator of not getting the perfect correction. And number two, hopefully, we should be able to both correct errors in the estimated likelihood ratio by essentially adding this alpha term. But at the same time, when we achieve and detect intransitivity, that should be some indicator that there's error going on. And so maybe we could also not only correct errors, but also detect errors. And that's exactly what we did. I'm going to skip this slide. This tells you about why the result is not intransitive. In terms of correcting errors, we tried this on both speech recognition and on a machine learning data set. These are results on a standard speech recognition data set for various vocabulary sizes, and found that the results for various vocabulary sizes get better, and which are significant at a high degree. And we also tried this on a number of the UCI machine learning, the UC Irvine machine learning data sets, and found that in many of the cases, basically whenever there was bold, we achieved a significant improvement. These are accuracies, so bigger is better. In some cases, the results were not significantly better, but in many of the cases, the results were significantly better, just by adding this alpha correction term. Okay. In terms of confidence measure, so we wanted to correct errors and also detect errors. Basically, detecting errors we were able to get by essentially looking at the length of the detected loop in the winner-loser digraph. So as the size of the loop that we detected in this large directed graph that shows who's winning over who in this pairwise classification scheme increases, so as the size of the loop increases, the probability of the error, where the error is measured according, of course, to the real answers, increases significantly. So this does seem, and in some sense, the length of the loop is in some ways a measure of the degree of intransitivity of the classifier. And so this sort of indicates that the degree of intransitivity does, in fact, correspond to error.
Is this the longest cycle?
This is the longest detected cycle. Yeah. So we don't have a way of assuring that we actually can detect the longest cycle. So it's an estimate. It's the longest found cycle. This is actually a difficult problem. It's an intractable problem to find all cycles in a directed group. So okay. So then the last thing about this was that since this is we were looking at this in a game playing strategy, we actually looked into the world of sports to try to see if there were anything that the people who knew about sports, if they could help us in any way. And we actually tried a number of different game playing strategies, such as a sequential tournament and a tree-based tournament, and random strategies. And we also tried a World Cup soccer strategy for trying to decide which classes to compare with each other, and found that basically looking at relative to the baseline, these are error rates again. We got an additional small, and in most cases not significant, but in some cases slightly significant, an additional small improvement by trying these game playing strategies, where either we try 500 random tournaments or 1,000 random tournaments, or use the World Cup soccer strategy, which actually worked pretty well in certain cases for these large number of classes. Okay. Okay, so the next thing I'm going to talk about is, in some sense, a combination of voice-based human-computer interfaces with speech and in machine learning. Okay. So this is a project entitled The Vocal Joystick. And the Vocal Joystick is joint work with myself and my students, and also Richard Wright and Katrin Kirchhoff, who are two professors at the University of Washington. And the idea is the following, that basically there's a significant population, subpopulation of individuals who don't have the use of their hands, or don't have the ability to to use things like a keyboard and a mouse. And there are a number of devices for these individuals that they can use so that they can utilize computers. And I don't know if you've ever seen these things, but has anyone ever seen a sip and puff switch or a head or an eye tracking mouse? Anyone seen this stuff? They're quite unwieldy. So the sip and puff switch is basically you're breathing in and breathing out to essentially indicate a binary pattern that tries to control something like a keyboard or a mouse. So it's very inefficient. Yet many of these individuals still have the use of their voice. And so they can, of course, use speech recognition. But when you're trying to control something like a mouse, or let's say that you're trying to control a robotic arm that has continuous movement, or a mouse which has continuous movement, or sliders which are inherently continuous, it's not really that efficient to use speech recognition. You can say things like, move second joint angle up by 30 degrees. Move it up again by 30 degrees. And it's a very inefficient way of moving mechanical or on-screen devices. And so what we've done is we've developed a system called the vocal joystick, which is essentially infrastructure that maps from the continuous control parameters of your voice to control signals, which can be used either to control something like a mouse, or, it's called the vocal joystick because it's supposed to be like a joystick, because you have essentially some continuous control parameters and some discrete control parameters as well, which is like a basic speech recognition system. And the continuous control parameters that we have looked at and we are currently mapping to consists of essentially vowel space. So depending on the degree of the vowel, you have at least 2 degrees of freedom in vowel space. There's also pitch, that gives you an additional degree of freedom, and amplitude, which gives you a degree of freedom. We're currently working on modulation and various derivative forms, which are in some sense independent of each one of these. So the voice can actually specify a large number of different possible degrees of freedom. And this is basically the block diagram of how the computation works. The motivating goal in building this infrastructure was to try to reduce computation as much as possible so that you reuse anything that can be used for, say, one thing like vowel classification that's also used for pitch estimation as well. And of course, there's also some, and this is sort of interesting, I'll talk briefly about this in a second. There's some work that we're doing on acceleration and adaptation in this domain. So I have a little video demo, and I don't actually have speakers here, but I'm hoping that this is going to work. This is a demo of one of my students who's actually using the vocal joystick for browsing the web. Yeah, hopefully it'll work. It's kind of jumpy. Doesn't normally look that jumpy. You can kind of see the mouse that's up here. There it is right now.
What is she trying to accomplish?
What is she trying to accomplish?
She's trying to point or
Well, let me pause it for a second. So what she's doing basically is there's a web browser,
yes.
and she's using vowels to basically move the mouse and using small sounds like a joystick to actually press and click on things. So she's using a, u, e, and ah to move the mouse either up, down, left, or right. And then basically the mouse is either you have a left button or a right button of the mouse, and she's using either k or ch to press on the button of the mouse. And she's actually gotten extremely good at it. So she can browse the web fairly easy with this, much to the dismay of her colleagues in the room that she shares. She's actually can browse the web just as easily as with a mouse. Now, of course, she's had a lot of practice with it because she's the one who has been developing it. But basically, it's quite feasible. And so for people who have either the vocal joystick as a mechanism or some sort of mechanism where you have to use the sip and puff switch or a head tracking mouse or an eye-gazing mouse. It's an interesting discussion, and I'd be happy to talk with you about it offline because we've actually got a lot more stuff to cover. But it's another dimension that you can actually control both web browsing and other sorts of things as well. Okay, so the next bit of stuff I want to talk about is graphical models in speech, language, and machine learning. So as some of you I'm sure are familiar, graphical models are basically a standard formal mathematical visual mechanism by which you can describe some important properties of families of probability distributions, and that's namely the properties of factorization. And what we've been doing is, because it's the fact that graphs cover a pretty large family of techniques, but at the same time, it's pretty easy to, once you've got an idea expressed in a graphical formalism, to communicate them to other people. You can actually very quickly get going with new ideas in speech and language and try out a lot of things. And so what I'll be talking about are some of the things that we've been trying out and some of the success stories that we've had. And then I'll also, at the end of the talk, describe, we've been working quite a bit on the algorithms of graphical models, because, of course, you want to be able to express things in this formalism. How do you actually express things in this formalism such that it's relatively painless from a toolkit perspective to do? So one of the things you might wonder is, where do graphical models fit into the world of machine learning? And the way I sort of see this is that you have this large machine learning area, and I think graphical models and kernel classification, or kernel machines and margin classifiers are basically, right now, two main components in machine learning. But in some strange way, they also sort of subsume each other, because within the world of graphical models lies kernel classifiers, and in that basically any implementation of an edge in a graphical model, you can basically use a kernel machine or a support vector machine. Yet at the same time, kernel machines have kernels over graphs, or kernels over hidden Markov models, or kernels over trees, or you can have parse kernels and so on and so forth. And so kernel machines also subsume graphical models. And I see them as sort of supporting each other, and they're sort of both an interesting side of machine learning. So this is a picture that some of you might have seen before, and this is just looking at a taxonomy of graphical models. And there are many different methodologies that graphical model subsumes, including things like, starting at the bottom, common filters, hidden Markov models, dynamic Bayesian networks, finite state transducers, input-output hidden Markov models, Bayesian networks, mixture models, decision trees, principal component analysis, linear discriminant analysis, simple models, conditional random fields, Markov random fields, autoregressive models, and so on and so forth. The list goes on. It's a big family of techniques, and so when you're working up here in this level of abstraction, you're actually working with quite a large set of potential things that one can use to implement and make your life easier and more fruitful. So I'm going to talk about a large number of different things that I've worked on in the past with respect to graphical models and speech and language, in both speech, in language, and then lastly I'll conclude with algorithms and toolkit results that we have. So this is graphical models and speech. For graphical models and speech, basically I've worked on taking hidden Markov models. This is an example of a graphical model for a hidden Markov model, and essentially looking and measuring the conditional independence violations made by that hidden Markov model by using mutual information, and essentially looking in a speech signal at pairs in either time, which is the x-axis, and feature position, which is the y-axis, and looking at basically where it is that essentially you have loss. Where is it that the hidden Markov model is not accounting for the particular dependency patterns that truly exist in the signal that ideally you should be looking at. And you can see that this is in some sense is a three-dimensional axis, because you've got, for any given time, you're averaging all over all time. You have tau, which is the relative position relative to the current time, and you also have I, which is where you are at the current time, and j, which is where you are at t plus tau. And so it's a three-dimensional axis, and when you project it down to 2D, this is, by the way, I should say this is on switchboard, which is a large vocabulary continuous speech corpus. When you project it down, this is now time lag along this axis, and this is difference in frequency in this particular case. There is a significant amount of information in speech that's not accounted for by the hidden Markov model. But then the other thing to realize is that, of course, what we're doing when we're doing speech recognition system is not necessarily minimizing loss in terms of unaccounted for dependency in the speech recognition system, but also we want essentially a model that discriminates well. We want a model that does well in terms of classification. And so we're interested not so much in fixing the loss, but basically finding some model that agrees with Bayes' rule, that basically says, okay, I'm going to make a good classification decision. My model F, I want it to make as good of a classification as the optimal procedure, but maybe I don't need to be as complicated as actually producing something which is optimal, which is the exact probability distributions for Bayes' decision theory. So the idea is try the simplest thing, to take the simplest thing that works. That's the basic idea. And the way in which you can sort of measure discriminative loss was defined by some work that I did at UAI in 2000, which is called the ear measure. And the idea here is that you're measuring the loss of a dependency, or in other words, the degree to which a dependency that's unaccounted for should be accounted for by looking at the difference between these two mutual information quantities, one which is class conditional, and it says, okay, I care about class conditionally a dependency between x and z when this guy is large, but if it's also large in the margin, if it's large unconditionally, then I don't care about it, which kind of makes sense, right? It's kind of like a posterior probability. You want the numerator to be large, and you want the denominator to be small, which is exactly this. You want this guy to be large and this to be small. And this is the motivation behind buried Markov models, which is basically a hidden Markov model that's been augmented by dependencies between successive observation features. And this was applied to speech recognition in a number of cases, and this is an example of the baseline hidden Markov model on a standard speech recognition set. If you measure the loss without the discriminative procedure, the error rate goes way up. And if you measure the loss using the ear procedure, the error rate goes down without any increase in the number of parameters. I've also looked at Gaussians as Bayesian networks, where a given Gaussian density can be represented as essentially a Bayesian network by doing a Cholesky factorization of the inverse covariance matrix in terms of, so K is the inverse covariance matrix. It can be factored into U du, where D is a positive diagonal of conditional variances, and U is the upper triangular matrix, the off-diagonal entries of which correspond precisely to the regression coefficients of a Bayesian network, which is represented right here. And so these are the off-diagonal entries of the U matrix, which are represented by B. And so whenever there's a B coefficient which is 0, you're missing an edge in a Bayesian network representation of that Gaussian. Okay. So the question is, what edges in a Gaussian should you use? And so this is an example of basically choosing edges based on in some nice way. So this is the x-axis is the number of parameters that you're using as a percent of the number of parameters that could exist in a fully saturated dense Gaussian, so a full covariance Gaussian with n squared parameters. Here, basically, this is on the left axis, on the left part. This is only n parameters. This is n squared parameters. And if you choose the parameters auspiciously based on mutual information, the word error rate decreases more rapidly than if you choose them inauspiciously or if you choose them randomly. Okay, so of course they converge to the same point because at the same point they have the same number, exact same number of parameters and the exact same models. Another thing that we've been looking at is, and this is much more recent, this is the use of virtual evidence in Bayesian networks, and this is something that Yuta Pearl came up with. And basically the idea is that you use an observed child to couple together parents in a way that essentially implements, it's sort of like a constraint function, but it's specified in a Bayesian network. And we've used this to specify a graphical model for pitch extraction. And this is work done by my students, Xiao and John. And I'm going to start skipping a little bit more, but basically by learning the costs for pitch extraction, learning the dynamic programming costs for pitch extraction, we're getting better results than at least the standard getF0 measure in ESPS, where we're getting better both gross error and also voice detection error rate. We're getting better results in both cases. We also have a model that we recently presented at ICASP. This is a new graph for both F1 and F2 detection. In this graph, we're getting better F2, the second format detection, but even though our format 1 detection isn't quite that good yet. But this is another model which uses this virtual evidence construct. This is a model that you're probably familiar with. This is a model that I co-designed with Jeff Zweig here at Johns Hopkins University at the O1 workshop. And this is basically a model that explicitly represents many of the things in the speech recognition system. Here's another one. The idea of these graphs is that you can represent pretty much any construct you want in a speech recognition system, whether it's a bigram or a trigram language model. One that we've recently been experimenting with is the idea of using a graph to represent tree-based lexicon, where you essentially share prefixes of words. And it's only by getting to the end state of some tree do you say, okay, I'm hypothesizing a given word as being spoken. And this is actually represented in this graph. And the idea of this graph, I mean, you don't need to understand the details. The idea of this graph is that you have this virtual evidence mechanism where you have this node here, which basically says that when a phone tree variable reaches the end state, it basically says that, and you take a transition out of that end state, this variable forces the next language, next word token to be equal to this, and that enforcement, that's being enforced by this virtual evidence token. So it actually works quite well, and we're actually decoding switchboard at this point with this graph. I'm going to skip this part. Another thing in graphical models in speech that we're doing is word-only acoustic features, where we have acoustic features which are attached directly to the word as opposed to attached to the phone. And this might sound a little bit strange, but it turns out that it makes a lot of sense, because if there are things that really have nothing to do with the phone but have a lot to do with words, like, for example, speech, non-speech detection, why should you force the phones to account for the variance in these features when essentially you're only, by doing that, adding noise to your system? So the idea is to have word-only acoustic features. And the procedure that we used here was, this is itself a little bit of signal processing, but the idea is, the intuition is very simple. It's basically that if you look at the entropy, the spectral entropy of speech in a time window, and you look at the mean and the variance of that spectral entropy, you'd expect that speech would be such that it has a high variance and a low mean, and for silence and noise you expect a low variance and a high mean. And that we found to be a very good indicator of speech and noise. And we added that, we added this feature, and we tried adding it just to the feature vector as what's normally done in a speech recognition system, and we didn't get any improvement over the baseline. But if we add it in this word-only kind of way, where it's only attached to the word, it's only affecting the word, then we get these significant improvements. This is on the Aurora 3 noise speech corpus, and you can see there's a lot of numbers here, but there's quite a bit of improvement. We've also been working on graphical models in language. Here's some work that we've done on basically learning string edit distance costs using dynamic Bayesian networks. This is work done by my student Kareem Filali and myself. And the basic idea is to treat edit distance as a stochastic process, where you have two strings, it's the source and the target string, and you have some probability distribution over an alignment between the source and the target, and that's basically done by essentially a sequence of hidden edit operations, which is the set Z. So we have some probability distribution over the source and the target by summing over all possible edits that yield a transformation between source and target. And we have various dynamic Bayesian networks for this. This is one, it's a little hard to see on the screen, but this is one that actually worked quite well. It actually has, it imposes a context, and so the edit operations themselves are conditioned on the context, which consists of both the source token at the current time and the source token at the next time. And this actually worked extremely well. Basically, this is, we tried this on pronunciation modeling, basically trying to map from surface phonetic forms to corresponding base form. And we learned the edit distance cost using these various models. Levenstein gets about an error rate of about maybe 35%. Some of these newer models, like this context model, did quite well. It reduced the error rate by 15% absolute. So this is just string edit distance learning, but this also has potential future applications and implications for speech recognition system. And I should say also that these service and base forms came from switchboard also. These are switchboard models. We're also applying Bayesian networks to language, including part of speech tagging with using this idea of virtual evidence again in negative training. The idea here is the following, that some of you might be familiar with taggers. You've got an HMM tagger. This is an example of a simple case where you only have a word and it is the word capitalized feature. The idea here is that this is a conditional Markov model. This is also a model that has been used for tagging before, but this one suffers from either label or observation bias because of the fact that these guys are independent of these guys, because it's a directed model. And we typically, there are a number of ways of accounting for label bias by using a conditional random field. And what we do is we actually introduce especially sort of this consistency variable, C. which is a virtual evidence variable, which basically couples together neighboring tags in some sense like an undirected way. But we're doing this purely within the framework of Bayesian networks, and so therefore the training time is still quite simple. And we came up with a training procedure for this. Again, I'm running out of time, but the basic idea is that C should be somewhat related to the mutual information between the tag pairs. So it's related to the ratio between the joint distribution between tag pairs and their marginals. But then we have a smoothing value, which is n. You might think, for example, that all you need to do is just set C is equal to 1 and then train, but that's not going to work because basically what that does is it says, hey, C is always equal to 1. Just give the probability of C is equal to 1 given these two tags. Let that equal to 1 for all cases. That doesn't do anything because that, once again, factorizes. And it's kind of like a bunch of independent tag classifiers for each word and feature. So here what we do is n is the degree of what we're calling negative training. And the more negative training, the essentially less we're basically doing what I just said, which is assuming that the probability of C is equal to 1 given the tags is equal to 1. And the idea, you can see that as n gets larger and larger and larger, the resulting probability approaches something that's proportional to this mutual information term. And if it gets, and as n gets smaller and smaller, it does more and more smoothing. Okay. And that actually worked extremely well also. We compared it to these are state-of-the-art results. Like here's this number 2 is, I think, the state-of-the-art result. This is Tutanova's and Dan Klein's work at Stanford. And they're getting about 96.55% token accuracy and 87.3% on the unknown word accuracy. Our best results are this case here. We're pretty much matching their token accuracy overall, and we're doing significantly better on the unknown word accuracy using this Bayesian network. So it's nothing fancy. It's not a conditional random field. It's just a Bayesian network with an appropriate factorization formalism. We've also tried these kinds of models to dialogue act tagging, and we have generative models for dialogue act tagging. And then the key question here is, what should this model be, the probability of the word given a dialogue act and a previous word? And we tried two different schemes, one of which is to use a switching n-gram, where for every dialogue act you basically switch between a different back-off language model of the words. And the other scheme we tried was a factored n-gram. This is something that was developed also as part of the O2 workshop here at Johns Hopkins, along with Katrin Kirchhoff. And basically we found that so I should say that the factored language model formalism has been actually added into our graphical model system. And we found that the factored language models significantly outperform the switching n-grams, particularly when we go to these higher order models, because the factored n-gram doesn't have this property that it splits the data and thereby leads to a great degree of data sparsity. We also tried a number of conditional models. Like here's one that has a pretty horrible label bias. We tried to account for the label bias by adding additional consistency, but in this particular case we didn't use the negative training idea I mentioned a few minutes ago. And some more conditional models, and found that in this particular case we saw pretty bad label bias in model 0, but then that was corrected by the virtual evidence scheme. But we didn't see any additional benefit in using the higher order model in this particular case. Okay, I'm going to mention a couple of results on, that are purely theoretical. The idea in graphical models is that you need to triangulate the model in order to get a junction tree such that you get a tractable inference problem. Interestingly, for models which have a combination, so what we're calling mixed graphs, models that are a combination of both deterministic and random edges, it is such the case that standard graph triangulation procedures don't work. They produce small cliques, but small cliques are not necessarily the best cliques. So the basic idea of this work was the following: that big cliques can be good cliques, number one, and some new triangulation heuristics that have the ability to find big cliques. And this is an example of where the triangulation consisting of this bundle and this bundle is unattainable using standard triangulation methods like the elimination algorithm. And so we have non-minimal triangulation methods which can achieve this triangulation. And this is then looking at our new triangulation methods just in terms of runtime. And in many cases, on random graphs and some real speech or language graphs, our new triangulation methods yield pretty significant speed-ups over the best possible triangulations that we were able to find using the standard methods.
Right, this is not runtime of triangulation.
This is the runtime of the inference after the triangulation has been performed. Right? So this is the triangulation time we care less about, because you do that once and then that cost is amortized over the life of the amount of time that you used the model for. So the best results are shown in bold. It's not always the case that we get better results. So in this particular case, the no extra edge heuristic case where it is a standard one. In fact, this is the edit distance graph. This is one of the graphs that I just showed you the results for a few slides ago. So in this case, one of the standard methods was able to beat our new method. But sometimes the results are quite good. So here's, I mean, typically we're seeing anywhere from 50% to factors of 2 to sometimes many factors. You know, this is like a factor of 7 or so. Okay. Another result that we have, which is purely theoretical, is the idea of pack learning bounded tree with graphical models. And the issue here is that, and the problem is that there have been a large number of negative results on structure learning and graphical models. Learning the best chain is NP complete. Learning the best K-tree is NP complete. Learning the best K-tree in certain cases approximately is NP complete. And what we've done is we have 2 results recently that are actually add to the very small number of positive results on learning structure, graphical model structure. And the basic idea is that, I mean, in this pack framework where you basically have an error and then you have a probability of being correct within that error. And in the pack learning framework, basically you just want to be polynomial in the number of samples and in the one over the error and then 1 over the confidence. And we can do that. And it's using basically, we really don't have time to go into the details of this here, but basically the key step, and this is sort of was the interesting realization about this, is that conditional mutual information is a symmetric submodular function. And it turns out that there is a recent algorithm developed by a mathematician named Quarian who developed an n-cube procedure for optimizing symmetric submodular functions. And so all we did basically was we came up with an approximate version of that algorithm that was able to achieve epsilon error. So it's the idea of epsilon submodularity. It still runs in n cubed. The idea of submodular, by the way, if you're not familiar with submodularity, it's basically a discrete version of convexity. And so convex functions, as you know, if a problem is convex, you can find the global optimum. And there are all these optimization strategies which are good for convex problems. Submodular is like a discrete version of convexity. So if you can prove that your program is submodular, then all of a sudden everything's great. So, and in fact, we showed this for mutual information. So there's a number of steps, but basically we came up with an algorithm which pack learns bounded tree with, meaning the resulting model that you get has bounded computation. That's what that means, essentially. And the algorithm runs in order n to the k plus 5. So with k being a constant, it's a polynomial algorithm in the size of the input, which is n. Okay. And we have another positive result, which is how to obtain optimal subgraphical models. And the basic idea here is this notion of just using dynamic programming. If you have, say, a bounded tree with graphical model and you want to find an optimal sub-bounded graphical model, like if you want to go from a k tree to a k-1 tree, then you can do so in polynomial time as long as you're not going down by too large of a step. And the basic idea here is this notion of what we're calling a separator tree, where the idea is that you start with, say, a junction tree representation of your bounded computation graphical model. And then you start where the nodes in the junction tree correspond to the leaves of the tree, and the non-terminal nodes of the tree correspond to the separators of the tree. And you start by doing dynamic programming up from the bottom of the tree, where you consider and what you propagate up are all possible, in terms of a set of constraints, all possible subgraphs of each one of those graphs that could possibly yield some part of that sub-bounded computation graphical model. And then what happens in each of these non-terminals is that you just look for the constraints which satisfy, and then you just propagate them up. And we proved that that can actually be solved in order n times k plus 1 to the d plus 1, where d is the step. So if you're going from a k tree to a k-1 tree, then d is equal to 1. So it's basically polynomial. So that's another positive result we have. And then lastly, in terms of graphical models applying to both speech, language, and machine learning, I want to end with talking about the graphical models toolkit, which is a toolkit that I've been working on for the past number of years, which also started as part of the 2001 summer workshop here at Johns Hopkins. And the idea here is that it's a software system for both speech, language, and time series modeling. It's, I should mention that all of the earlier graphical model results that you saw were all run with GMTK. So there's just an enormous number of research issues in how to get GMTK to run and how to get GMTK to run fast and what are the algorithms associated with it. And there's quite a large number of features, at least 26, and actually there's more. It's 27 to 37. I'm not going to go over all 37 of them. I'm just going to talk very briefly about 3 of them, in fact. So there's a standard textual programming language with which you can program in this graphical way. There are some new ways. So basically, since the 01 workshop, GMTK has been completely rewritten. And it's now much faster. And in fact, our best improvement right now is about a factor of 800 over the one that was used in the 01 workshop. So it's significantly faster. And the reason why it's faster is because there has been a lot of work on just the inherent algorithms that we're running. We're using completely different algorithms. And one of the ways that the algorithms are new is basically on using this idea of separator-driven interface, where we essentially it's basically, in some sense, standard junction tree interface, but it's done in a very different way, where we don't actually even look at and consider what's going on in the cliques until the separators have already been ready. And I think the best way to do it is to just describe it in terms of pictures, where let's say that we're trying to create this clique function and we have these separator functions. The way it's normally described in the literature is that you, for example, sum over the clique, and then once you've got this, then you multiply in these separators. Doing that just is extremely slow. It just doesn't work very well. And so what we do is instead, we build the separators with respect to each other. So they actually have knowledge of each other, meaning that when we build this separator, which has variables a, b, c, we would build the next separator with knowledge of the fact that we've already seen a, b, c. And so we would basically be able to hash into this separator based on what was common with this separator, and then iterate over the residual, which is d. And the same thing here. Basically, this separator is de. We'd hash into based on what's in the union of the previous separators, and then iterate over only the residual. And then after you're done with all of this, you have what's guaranteed, at least according to the separators, to be something which is not giving you 0 probability. Because the 0 probabilities you want to get rid of as soon as possible. Then we go into the clique and continue on inside of the clique. And that gives you a huge speed up. There's a number of issues of how do you choose the order of the separators. And so what we're doing is using a dynamic programming algorithm to find the optimal order. That's done offline before inference is done. The other nice thing about this is that it allows for approximate inference to be performed using something that can essentially be seen as a generalization of what people use in speech recognition in terms of beam pruning. And so that works quite well. And then lastly, the last one of those 37 topics I want to mention is this almost optimal pack representation of cliques. And something that turned out to be a huge win, and this might in some sense sound trivial, but it turned out to be a huge win, was just basically by packing clique values. So the idea is maybe you have a bunch of variables that you want to represent as an array, and normally you would use 32 bits for each one of these variables. And so in this particular case, for k values, you would need k times 32 bits to have as storage for every single clique entry, and there can be an exponential number of clique entries. And so the idea here is that we instead, of course, we pack everything together in terms of its bit patterns. And so we can have, for example, this guy, which takes, in some sense, it has a capacity only of 24 bits. We pack it into one 32-bit machine word. And as you know, operating and manipulating single machine words in modern microprocessors is quite fast and much faster than doing multiple machine words. And basically, we want to pack things into as tight a region as possible. Now, the interesting thing about this, however, comes about, which is that when you're packing things into a succession of machine words, and this is a real systems optimization level, basically you want to try to minimize the number of words that split, word boundaries that split a given operand. Because in that case, basically what happens is all of a sudden your branch prediction logic is broken. And so it turns out that it's an NP-complete problem to find the optimal packing. It's actually very similar, if anyone's familiar with the stock cutting problem, which is what people who are trying to decide what the best way of cutting reams of paper for customers is. And so so it's an NP-complete problem, but we actually have a heuristic procedure which finds a almost optimal bit packing pattern, and that basically, in most cases, means that there's no branch prediction penalty. So we don't pay any additional cycle penalty by mispredicting a branch inside of this packing procedure. And you might think this is kind of crazy to do this, to worry about branch prediction, but this is way, 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 way down in the innermost loop of inference. And so it's really crucial for this to be as fast as possible. So this is another thing that has had a big win. Yep?
You're 20 minutes over time.
Okay, I'm done. That's the summary. It's a lot of stuff, and I know, but hopefully there's something in there for everybody. Any questions? Yep.
Well, here's a nice, easy, accessible one. In the voice-based interface,
Yep.
Sorry, the voice joystick,
Yep.
it looks like the user wasn't making any use of pitch.
In that particular case, yes. So basically, when you're doing mouse movement, it's just doing up, down, left, right mouse movement. Right now, what we're doing is vowel space. And we actually have a version that's running. In fact, when we first implemented it, we actually used pitch for height and amplitude for left and right. And that didn't work as well as being able to use e, ah, u.
Meaning users didn't like it as much, or you have some
It was harder to control.
Yeah.
And we're not entirely certain as to whether or not that was because the pitch extractor, which is the reason why we're doing this pitch extraction, to try to get better pitch extractions. We weren't entirely sure whether that was due to the fact that pitch extraction wasn't as reliable as vowel classification, or if it was the case that for some reason, and there's a lot of human factors associated with this new interface. So unlike a mouse, a mouse is sort of natural in the sense that you're mapping space to space, right? Here what you're doing is you're mapping things that have no spatial correlate to space. And so what's the right mapping to map from these non-spatial things to space? And so that's where a lot of the human factors research is coming into play. And we're doing a lot of experiments. These have to be done by user experiment, which is very similar to, one of the things we're doing is we're actually going back and reading a lot of the original early mouse papers from the early 70s. And a lot of the things that people were doing were experimenting with different acceleration schemes, with different adaptation schemes. And the only way to evaluate is to have users come in and ask them and query them.
Is there a way to get feedback?
Formally?
No, I'm sorry. I don't mean about feedback in the evaluation. I mean in terms of adapting the mapping between vocal space and mouse space. You might have some prior model of what kinds of trajectories the user is likely to be preferring.
Yes. Well, we have so right now currently what we have is a function which basically consists of a combination of a polynomial trajectory and an exponential trajectory and a linear sort of constant trajectory. And the user can, at this point, adjust the parameters on the command line to find the best mapping. But it's still not where we want to be because right now it's too many parameters to adjust. And so what we're trying to do is find essentially the crucial smallest set of, maybe if there's one slider that they can adjust, which basically gives them. But what's interesting is that it's actually vowel dependent. It's not only person dependent, but the warping that you want for one vowel is not necessarily the same as you want for a different vowel. Because vowel, and for example, take energy itself. Like energy, our perception of energy is different depending on what vowel we utter. And so for example, like oo is and ah versus e and ah have different inherent energies. It's almost like a production Fletcher-Munson curve. And so that itself needs to be taken into account as well. So.
Are any of the speech results on large vocabulary?
So one of the things, and one of the reasons why there's been so much research done in high-performance computing is because these models, are computationally difficult. And we are currently, at the moment, literally decoding large vocabulary results for the first time. So none of the results that I presented are on, say, Switchboard or Fisher. But I'm confident, so the one result I showed about these word-only features, I have a feeling that that's going to, it's way back there. I can find it again. So the one case where you had the acoustic features hanging directly off the word, I believe that should have a significantly beneficial effect for things like Switchboard. Like there are all these standard ways of measuring prosodic information in speech, which is something that's common in conversational speech. And typically what people have done is they've added them to the feature vector and forced them to be explained by these phonetic sequences. And again, so what you're doing there is if the correlation is indirect, if the correlation between the new acoustic information that you're getting is really only with respect to the word, and you're forcing it to go through this expansion in terms of these decision tree clustered triphones, what you're doing essentially is you are reducing the amount of data that each parameter for each one of these triphones accounting for this feature has, which therefore increases variance, increases noise. And so I think that adding them to some higher level in the speech recognition system will be beneficial. So.
How many students do you have? This looks like 500.
506.
No,
Well,
but seriously.
right now I have 8 students.
I see. Okay, so certainly you listed many more names.
Well, some of the feedback work was work I did a while ago. That was,
Okay.
So in the large vocabulary task that you were mentioning, is the training done by GMTK or you just do it outside using HTK?
No, the training is done by GMTK. And we find that, in fact, GMTK does better than HTK for training in particular, quite a bit better. And in terms, it produces better Gaussians, even if we're just simulating an HMM.
Well, thank you very much. I don't know what you said. They showed me the schedule again.
I think I have it.
Oh, so you